As we begin chapter 7, we're going to be talking about exponents and exponential functions. We're going to be looking at real number systems, seeing structures and expressions, linear, quadratic, and exponential models. So, as you look in your textbook, you're going to look at this picture of bacteria population. And as you're looking at this, we want to think of all the different colors you can see around that screen. So, looking at the chapter, um, did you know exponents describe the growth of a population? Here are some of the words that we're going to be working with, and as you look at your vocabulary sheet to fill in. Some of the big ideas for this chapter that we're looking at is zero and negative exponents. Properties of exponents is going to be in lesson 7.2, 7.3, and 7.4. We're going to look at what's called our rational exponents and radicals. So you'll notice that they have fractions as you look at your review. And then exponential functions in 7.6 and 7.7. And then last but not least, we're going to look at geometric sequences. In lesson 7.1, the key thing that we are going to be taking a look at is zero and negative exponents. And as you look at this table, one of the things you want to be thinking about is what's happening in the first columns as the exponent decreases by 1. So 2 to the 4th, if we are looking at what that is equal to, 2 to the 4th is equal to 16. We have 2 to the 3rd equal to 8, 2 to the 2nd, 4, 2 to the 1st is 2. So as we look at this column, it looks like each time we are dividing by 2 as we go down that column. What's happening in the second column? Well, 10 to the 4th just simply means that when we are looking at 10 to the 4th, we're looking at a 1 followed by 4 zeros. 10 to the 3rd is a 1,000. We had 10,000, 1,000, 10 to the 2nd is 100. 10 to the 1st is 10. So we would think as we continue both of these patterns, if we continue dividing by 2, we would have 1, and then 1 divided by 2 gives us 1/2, and then 1/4. Here again, we have 1, we have 1/10, and we have 1 over 100. So as you look at this, how are 10 to the 2nd and 10 to the negative 2 related? They are actually going to be what we call our reciprocals. So those two are reciprocals. Now, you should be filling in the vocabulary in your notes, but the rest of the notes you may either want to take on a sheet of notebook paper, or you want to do it in that foldable notes that we talked about. The key thing that you understand is that when you extend the idea of exponents, including zero and negative exponents. So the rule for zero as an exponent is that for any non-zero number a to the 0 always equals 1. So here you have 3 examples that are all equal to 1. When you work with negative exponents, the key thing with negative exponents is that for every non-zero number a and the integer n, a to the negative n is written as 1 over a to the n. The other way of thinking about this is that if you have 1 over a to the negative n, it moves it, if it's in the denominator, to make it positive, you're going to have a raised to the positive n power. So as you're looking at these different problems, to make an exponent negative, if it's in the numerator, you're going to move it to the denominator. If it's in the denominator, you're going to move it to the numerator to make it positive. Here's some key things that you want to think about. Why can't you use 0 as a base for 0 exponents? Well, if we think about what this property implies, anything to the 0 power should be equal to 1. But when we take 0 to the 3rd, it's 0. Same with each of these, 0 to the 2nd, 0 to the 1. So therefore, 0 to the 0 power cannot be equal to both 1 and 0. Therefore, it is undefined. As we are looking at this, why can't 0 have a negative exponent? Because when you use 0 as a base, the negative exponent results in division by 0, which is undefined. Here is problem 1 that you want to put in your notes. 9 to the negative 2. What is 9 to the negative 2? Well, using our definition, we're going to rewrite that as 1 over 9 to the 2nd. 9 to the 2nd is 1 over 81. Part B that you put down in your notes, negative 3 to the 0. Anything to the 0 is 1. What I would like you to do right now, and we're going to do these in class, is to try and find what these 5 answers are as you are taking a look at the got it problems. Something to keep in mind, why is 9 to the negative 2 not considered simplified? We're usually going to have a numerical expression is not considered simplified until the form of the operation can be done. So in this case, this is not a simplified problem until you get 1 over 81. In example 2, that you're going to put in your notes, find a to the third and b to the negative 2. The first thing our definition says is we want to rewrite this with a positive exponent. So we're going to have 5a to the third times 1 over b to the second. Now a lot of times we could just write that right away as 5a to the third over b to the second power. When we have 1 over x to the negative 5, if it's in the denominator, we're going to move it to the numerator. So x to the negative 5 becomes x to the fifth over 1, or simply x to the fifth. I would like you to try it now with these problems. Pause the video if you're watching, try it, and then take a look at the answers. And you should have had these solutions. When you evaluate exponential expressions, you simplify, and as we are doing that, as you're simplifying, the expression before you substitute in your values. So as we are taking a look at this problem, one of the things you're asked to do is to evaluate. But if we simplify it first, we're going to rewrite this, and as we rewrite it, we are looking at it as the only thing that's negative is a t. So we're going to have 3 and s to the third power, all divided by t to the second. If we look at that expression and we start substituting in, we are going to have now 3 times 2 to the third and negative 3 to the second. And if we think of what that equals, that's 3 times 8 divided by negative 3 squared gives us positive 9. I would simply simplify at this point first, and we end up with a solution of 8/3. Now they also show another way is that you could substitute first. And this also works as you're doing the problem. You're still going to apply your rules, and you still get the same solution of 2 2/3, or if we are looking at that, of 8/3. As you look at each of these in the got it part, what I want you to think about first is, as we look at the problem, if we are simplifying it, as we simplify, rewriting it first with using our rules of positive exponents. So we actually have w to the 0, which is 1 over n to the 4th. The second one, we would have 1 over, we have w to the second, and our n would be to the first power. As we look at the last one, n to the 0, we are looking at that as simply 1. We would simply substitute in our 5 to the 6th power. Here, since n is to the negative 1 power, the w is to the negative 1 power. It's going to move to the numerator, w to the first over n, which would simply be our 5 divided by negative 2. Something to think about. Is it easier when you're looking at n to the 0 and w to the 0 to first substitute, or could you use your rules first? So do you want to evaluate it first or substitute? Myself, if I'm looking at this, anything to the 0 power is equal to 1, and 1 times 1 equals 1, and I would not substitute if I didn't have to. The last part is using exponential expressions when we're looking at a problem. So if the population of the marine bacteria doubles every hour under controlled laboratory conditions, the number of bacteria controlled by the expression starts out at 1,000 times 2 to the h, where h is the number of hours after the scientist measures the population size. If you're going to evaluate h to the 0 and h to the negative 3, what does each value represent? Well, first thing we're going to do is write out our expression, 1,000 times 2 to the h, which in this case, 2 to the 0, which equals 1,000, which simply means our answer is 1,000, and that means that there were 1,000 bacteria at the beginning at time 0. 1,000 times 2 to the h at negative 3 means that as we substituted in negative 3 for h, we end up with 1/8 equals times 1,000, which equals 125. What that's telling us is that the value 3 hours ago, there was 125 bacteria before they started this. As you look at this next part, the population triples every week. The number of insects modeled is 5,400 times 3 to the W, where W happens to be the number of weeks after the population is measured. You're asked to find W of negative 2 and W0 and W1. It says, what does each of these values represent? Well, we know if we're looking at our time, we're going to have 5,400 times 3, and if we have to the negative 2 power, that's going to be 5,400 times 1 over 3 to the second, which is the same as taking 5,400 and dividing it by 9. If we look at the second one, 5,400 times 3 to the 0 power, that's simply telling us that at 0, and in this case, W represents weeks, at 0 weeks, we're going to have 5,400 insects in our population. At 5,400 times 3 to the 1 means we're going to take 5,400 times 3 because it's tripling. If we are looking at when they talk about in the Goddard, what is the effect if we're having a value that is greater? If we're looking at our value here, a greater value of W in the population, a greater W of W is going to give us a larger population. So when W happens to be 1, 2, it's getting larger. And what happens when it's negative is that the population approaches 0, but it's never going to reach it as we look at that one. We are going to start your homework with these problems, so good luck, and if you have more questions, please make sure you stop in and talk to me so I can help you out.